These are some of the world's major cities: New York, Tokyo, London, Hong Kong, Buenos Aires. They look much like any city in the United States, don't they? Big buildings, bright lights, crowded streets and highways. Busy people engaged in high-tech business and industry. Today's businesses are not just nationwide. They have offices and interests all over the world. And I'm proud to know that my telephone was a major factor in the development of this worldwide economy. The telephone network makes it possible to send voice and data instantly, no matter where the company's offices are located. As good as this worldwide telecommunications network is, there are plans afoot to make it even better. It's a concept called ISDN. In the next few minutes, you'll be introduced to ISDN and learn some of its basic characteristics. You'll see ISDN customer premises equipment, CPE, and learn how it differs from traditional CPE. We'll compare traditional and ISDN call processing. And finally, we'll look at ISDN capabilities and applications today and in the future. Let's begin by defining ISDN. ISDN stands for Integrated Services Digital Network. ISDN is hard to define in a single statement. There are two ways of looking at it. First, let's look at its broad network definition. Remember that ISDN is still being implemented and will be for many years. Broadly speaking, when its evolution is complete, ISDN will be an international public telecommunications network that will provide end-to-end digital connectivity and integrated access to both the public telephone and packet networks. Now, much of this network, however, presently exists. Some of it is being implemented following plans that were made before ISDN was conceived. The only part of the ISDN network that is really unique to ISDN is the interface between the user and his or her central office switch. From this more narrow perspective, ISDN is a set of protocols that defines how voice and data can be communicated simultaneously over the existing local loop, and that provides the user with integrated access to both the public switch telephone and the public packet data networks. Any equipment developed in accordance with these protocols for the purpose of implementing this interface between the user and these networks. Any telecommunication user services, whether existing or new, that are available to ISDN customers over this interface. Try to keep both perspectives in mind. ISDN as a network and as an interface as we tell you more. Let's begin by looking more closely at the international nature of ISDN. In a previous program, we discussed the concept called Open Systems Interconnection, or OSI. You remember that Open Systems Interconnection is basically a set of internationally agreed upon protocols that specify how networks communicate with each other and the characteristics that the CPE must have in order to attach to a network. OSI, and more recently ISDN, came into existence and have been developing with help from a number of national and international organizations. Three of the most important are International Telegraph and Telephone Consultative Committee, CCITT. This is a United Nations organization that recommends standards for international telecommunications. International Standards Organization, ISO, which recommends data standards. The OSI concept was developed by ISO. American National Standards Institute, ANSI, which applies standards within the U.S. There are literally dozens of protocols that have been recommended by the standards organizations and accepted by the telecommunications industry over the years. For example, in 1984, the CCITT published a major reference of ISDN protocols, referred to as the Red Book, and they published another, the Blue Book, in 1988. Using these publicly available protocols, any competent electronics manufacturer can design, build, and sell devices that will work with the network. This stimulates competition between manufacturers and encourages the development of new applications for ISDN. You learned that the Open Systems Interconnection Reference Model, which is usually referred to as the OSI model, guided the development of most of these protocols. The OSI model defines a hierarchy of 7 different levels that must be considered in order to communicate something over the network. The most important layers for us are the bottom 3. The physical layer. Protocols at this layer define the physical characteristics, for example, voltage, of the signals. The data link layer. These protocols define what information must be communicated in order to establish links between network devices. The network layer. Network layer protocols define what information must be communicated to establish end-to-end contact between customers. ISDN is an outgrowth of open network architecture. It is more limited in scope than ONA. ISDN is primarily concerned with the network interface, which is the interface between the CPE and the central office switch, rather than the interconnections between networks. There is a set of standards called the Iseries Protocols that deal specifically with ISDN. They specify the physical, data link, and network layers of the ISDN network interface. We will be talking more about these protocols later in this program. However, ISDN is intended to work within the existing network structure, so its protocols must support or be consistent with existing protocols, especially at the network level. Some of these, like the packet network protocols X.25 and X.75, you've already heard about. That's enough for now about protocols and the international nature of ISDN. I said that ISDN stood for Integrated Services Digital Network, and that the digital network was, in fact, end-to-end. What do we mean by end-to-end digital network? We know that in today's public switched telephone network, digital switching machines are replacing the older analog switches. However, even if your central office has a digital switch, your local loop may still be analog. If your CPE is a telephone, its analog signal is converted to digital when it enters the switch. If your CPE is a computer, its digital signal is converted to analog by a modem, and the signal is converted back to digital at the switch. ISDN telephones convert your voice directly to a digital signal. The digital signal from the telephone or your computer travels the local loop to the switch, where it can be processed without any conversion. Even though the ISDN telephone looks similar to a modern analog telephone on the outside, internally they are very different. For this reason, many people don't use the term telephone when they refer to it. They prefer the terms voice terminal or station set. We'll call them voice terminals. In addition to generating a digital instead of an analog signal, ISDN voice terminals are different in other ways. The ring and the various tones, like the dial tone, and busy signals are generated in the voice terminal, not by the central office. The power to operate the terminal is provided by the customer, not the central office. The terminal and the central office are always sending signals to each other, even when the terminal is on hook. We've talked about what we mean by digital network, which is the DN in ISDN. What about the IS, which stands for Integrated Services? Just what are these integrated services? The most general answer to this question is to say that Isdn services include any services that can be offered over either the public switched or packet networks. The ISDN user has easy access to both without the need for special connections. New switched and packet services are being invented all the time, but at present the ISDN user can send or receive voice, high-speed circuit switch data without the need for a modem, either low or high-speed packet data, telemetry, for example, for remote alarm or environment monitoring and control, high-speed facsimile, including the rapid transmission of high-resolution pictures and graphics, slow scan video. Now, these services are all available without ISDN, but the ISDN subscriber can have them with specially conditioned lines over the existing local loop. And with ISDN, different services can be used at the same time. I can be talking and receiving data or sending a fax all at the same time. I can have several different devices simultaneously connected to and sharing my twisted pair local loop. So, that's the basic picture of ISDN. It's a worldwide communications architecture that grew out of an open network architecture. It's defined by a set of protocols that were developed by the CCITT and ISO. ISDN is based on the 7-layer OSI reference model. The ISDN protocols are concerned with defining the interface between customer and the central office switch. This allows the customer to access simultaneously both circuit and packet switch digital services using the existing local loop. It's going to have a large impact on how we do business and how we perceive the telephone. Please return to your computer to continue this lesson.
In the previous program, you learned that ISDN boils down to a set of circuit-switched or packet services that the customer can use at the same time. Here's a question for you. If you walked into someone's office who had ISDN, would you be able to tell by the equipment if ISDN was present? Does ISDN require special equipment? In this program, we'll examine that question. We will discuss the functional groups of ISDN Customer Premises Equipment, CPE. We will also talk about the reference points that define the connections between these functional groupings. We'll introduce you to the channel arrangements available with ISDN. And finally, we'll tell you about a concept called multipoint. First, let's define the different functional groups and give you examples of the equipment included in each. There are 8 functional groups that make up the ISDN CPE network interface. Let's begin on the network side and work toward the ISDN subscriber. This first functional group is called the exchange termination, or ET. The ET is the digital switch at the central office. This digital switch provides the ISDN customer access to the public switched telephone network. The second functional group, called the packet handler, or PH, provides the customer access to the public packet data network. Depending upon the manufacturer, the actual packet handling equipment may be part of the switch and can be classified as one functional group, or it can be totally separate equipment in a different location. In this case, the ET and PH are usually connected by DS1 transmission facilities. The point at which the ISDN subscriber's local loop enters the switch is called the line termination, or LT. In most digital switches, the line termination functions are performed by a line card, or line circuit card. There is one line card for each local loop. The fourth functional group, called a Network Termination 1, or NT1, is located at the subscriber's end of the local loop. The devices that belong to this functional group are also called NT1s. Sometimes the NT1 circuitry is built into another device. In the United States, NT1s are owned by the subscriber rather than the telephone company, so they are the first devices that can be called customer premises equipment. The job of the NT1 is to convert signals from the customer's CPE. These signals need to conform to the ISDN physical layer protocol. The NT1 also performs 2-wire to 4-wire conversion because the CPE signals are transmitted over 4 wires, and the local loop is 2 wires. Occasionally, the local loop has 4 wires. In this case, the NT1 is not used. Usually, NT1 is connected to only one terminal, although by using a passive bus, up to 8 devices can use the same line. The network termination 2 is a true multi-terminal device. NT2 devices include digital PBXs, terminal controllers, and local area networks. NT2s concentrate, switch, or multiplex the subscriber's internal lines onto one or more local loops. This is the heart of a digital PBX that has 80 internal lines. It has 20 trunks connecting to the central office via an Isdn arrangement. Because of Isdn, these 20 trunk channels can be carried on one local loop connection. Without Isdn, it would take 20 separate wired paths or special multiplexing equipment to connect the trunks to the central office. The next functional group, Terminal Equipment 1, or TE1, includes devices that are designed to meet the OSI physical, data, and network protocols. These devices are called Isdn compatible because they can be connected to an NT1 or an NT2 device without needing an adapter. Another subscriber may not need an NT2 because he does not have many voice terminals or data devices that must share the Isdn service. In this case, the TE1 device can connect directly to the NT1. Note that this subscriber's line termination device, the line card, is not in the central office but in a remote location. This voice terminal is one example of a TE1 device. It plugs directly into an NT1. It could also be used with an NT2 device such as a digital PBX. The final 2 functional groups are Terminal Equipment 2 and Terminal Adapter. TE2 devices are not Isdn compatible, and so they need TA devices to convert their output to the Isdn protocols. The TE2 device connects to a TA device, then the TA device connects to an NT2. The TE2 can also connect, through its TA, directly to an NT1. Most personal computers are TE2 devices. They must be connected to a terminal adapter, like this one. Then the TA is connected to an NT1 or to an NT2. Also, some voice terminals have built-in terminal adapters so that TE2 devices can connect directly to them. To review all of this, remember that there are 8 functional groups. 3 of them, the exchange termination, packet handler, and line termination, are devices that belong to the telephone company. The other 5 are customer premises equipment. In a 2-wire loop, your CPE will always include circuitry that performs the NT1 functions, but it may or may not have a separate device called an NT1. Your CPE may not have any NT2 devices. TE1 or TA devices can connect to the NT2, or directly to the NT1, or directly to the LT with a 4-wire loop. Well, you've now seen examples of the equipment in each of the 8 functional groups. But there's one more type of equipment that isn't in any of the functional groups. However, if you walked into someone's office who had Isdn service, you might very well see it. The type of equipment I'm talking about is the power supply. Remember, the telephone company doesn't provide power to the voice terminals or to any of the other Isdn CPE. This equipment can't use the regular 120-volt AC power directly, so power supplies are needed to convert the power into a voltage that they can use. This is one common type of power supply. I'll refer to it as an external individual type because it is a standalone unit designed to power one voice terminal and its NT1. In many Isdn installations, one standalone power supply in a central location can power a number of voice terminals, NT1s, and other CPE. I'll call this type the external central type. Note that in this installation, the NT1s are also located centrally. The third type of power supply may be the most common of all, but it's also the easiest to miss because it's built into the equipment it powers. This is the internal type of power supply. Most TE2 devices, like this computer, have internal power supplies. Most NT2 devices will also have internal power supplies. So far we've talked about the functional groups and their power supplies. Now let's talk about the connections between the functional groups. They're called reference points. The ISDN reference points are identified as letters, the letters R, S, T, U, and V. R refers to the interface between the TE2 functional group, the non-ISDN compatible equipment, and the terminal adapter functional group. S is the interface between either the terminal equipment 1 or the terminal adapter and the network termination 2. The T interface is a 4-wire loop between the network termination 1 and network termination 2 devices. If an ISDN subscriber does not have an NT2 device, the T reference point connects the NT1 directly to the TA or TE1. The U interface is a 2-wire loop between network termination 1 devices and the telephone company's line termination device. Finally, the V reference point connects the line termination and the exchange termination devices when the LT is located in a remote location. Physically, the V reference point is the same as a DS1 transmission facility. At this point, you may be asking yourself, why are functional groups and reference points important? The answer is that they define the structure or architecture of the ISDN network. Let's talk about the Isdn services that are available using this architecture. To do this, we'll move on to the third topic of this program, ISDN channel arrangements. In the non-ISDN world, the subscriber accesses the public switched telephone network by means of his local loop. If this subscriber wants to send packet data, he can use the local loop and the switched network to dial into the packet network. This subscriber could also attach a fax machine to his local loop. The local loop, however, normally carries only one channel. You can have a voice call, send a fax, or send packet data over your local loop, but because you have only one channel, you couldn't do these things at the same time. If this subscriber has the need to move lots of data, he can have a separate line permanently wired between computers. This is called a dedicated access line or a private line. In contrast to this, ISDN equipment is designed so that they share the local loop. In effect, they create more than one channel over the local loop so that multiple calls can occur at the same time. Even high-speed data that used to require the dedicated access line can be sent and received using one of these channels. At present, there are two ISDN channel arrangements available. One is called the Basic Rate Interface. We'll also refer to it by its initials, BRI. The Basic Rate Interface can have up to 3 channels. The first type of channel is the B or bearer channel. You can have up to 2 of these per BRI. Both of these channels can carry voice and circuit switch data at a bandwidth of 64,000 bits per second. They can carry packet data at 19,200 bits per second dial-up or 64,000 bits per second if the channel is dedicated. The second type of channel is the D or delta channel. This channel transmits at 16,000 bits per second the signaling information that sets up, monitors, and disconnects all calls. It can also carry low-speed packet data at 9,600 bits per second. There is only one D channel per BRI. BRI is the channel arrangement that provides multiple channels over the existing 2-wire local loop. Remember that while you always must have the D channel, you will not always have all the B channels. For example, a BRI subscriber can order 1B plus D or 2B plus D. The other channel arrangement is called the Primary Rate Interface, PRI. It can have up to 24 channels. One type of channel on the PRI is the B channel. You can have up to 23 B channels per PRI. B channels transmit voice and circuit switch data at 64 kilobits per second, or it can also transmit dial-up packet data at 19.2 kilobits per second. The second type of channel is the D channel. You will have one D channel per PRI. This channel has a 64 kilobits per second bandwidth for signaling, much more than the bandwidth of the BRI D channel because it handles many more B channels. The PRI D channel can also carry low-speed packet data at 9,600 bits per second. The PRI arrangement requires a 4-wire circuit between the NT1 and the TE. It is the same as a DS1 transmission facility. One other type of channel, the H type, will soon be available for PRI, These H channels will provide users with higher bandwidths than the B channel. Basically, H channels are combinations of B channels. For example, two of the H channels already defined are H0, which is 6 B channels combined to provide a bandwidth of 384,000 bits per second. H11, combining 24 B channels to provide 1,536 kilobits per second. That's 1,536,000 bits per second. With the H11 arrangement, the D channel would have to be in another PRI because the H11 channel fills the entire PRI. The PRI customer has at least one D channel and combinations of B or H channels. He might have, for example, only 10 B channels plus a D channel, or 2 H0 channels plus 11 B channels and a D channel. A third choice could be one H11 channel. The customer will need another PRI service to accommodate this D channel. It will soon be possible for the ISDN customer to dynamically allocate bandwidth as needs change. For example, a PRI customer could substitute one H0 channel for 6 B channels in order to transmit high-speed data at 384 kilobits per second, then change back when the transmission was complete. We've been emphasizing that with an ISDN channel arrangement, several devices can be sending and receiving voice or data at the same time. Let's finish up this program by looking more closely at this concept, which is called the Isdn multipoint capability. The multipoint capability has to do with the fact that each BRI service can support multiple devices. A BRI user can have up to 8 devices attached to his NT1, and all will share the BRI. One device can be sending and receiving over each B channel, and up to 6 devices can be sharing the D channel. When the D channel is not needed to send signaling information, the D channel devices take turns sending and receiving packet data at 9.6 kilobits per second. It's about time to summarize what we've covered in the last few minutes. The title of this program is Basic Concepts and CPE. We began by describing the 8 functional groups and the kinds of CPE that are included in each. Then, we reviewed the 5 reference points that identify the interfaces between the functional groups. After that, we covered BRI and PRI, the 2 channel arrangements now available for ISDN customers. Finally, we examined the multipoint capability. In our next program, we'll look at ISDN signaling in greater detail. That concludes this program. Please return to your computer to continue the lesson.
So far, we've talked about what ISDN is, its background and important concepts like function groups and reference points. You've seen examples of customer premises equipment, CPE. Now let's learn how ISDN works. In this program, we'll begin at the physical layer and describe what the signals look like that transmit information between the CPE and the central office. You will learn how several CPE devices can share this transmission path. Next, we'll talk about what information is necessary in order for a specific CPE device and the central office to establish a communications link and how this information is organized into frames. Let's begin by defining a typical ISDN service. Lynn Jones and Jim Smith are sales representatives for several manufacturers of industrial equipment and supplies. The business is small, but they have several major accounts that place their orders over a computerized system that uses the public packet data network. Lynn and Jim also use the packet network to place orders to their suppliers. They each need a voice terminal and a personal computer to negotiate and process orders, plus they have a third PC for their clerk. This is a diagram of the Smith & Jones Company Isdn service. They have a BRI channel arrangement that provides 2 B channels and 1 D channel over their 2-wire local loop. You remember that the connection between the line termination and the NT1 is called the U interface. The 3 computers are not Isdn compatible, so they are each connected to a terminal adapter. The 3 terminal adapters and the 2 voice terminals connect to the NT1 over the same set of 4 wires, called a bus. As you remember, the connection between a terminal adapter or voice terminal and the NT1 is a T interface. You may also recall that the S and T interfaces are basically identical. For these reasons, this 4-wire connection is usually referred to as the S or T bus. To understand how Lynn and Jim's Isdn service works, let's first look at the nature of the signals that pass over the S or T bus and the U interface. If you remember the OSI reference model, we'll be talking about layer 1 of the model, the physical layer. The type of digital signal that all the devices on the S or T bus use to transmit and receive information is called inverted AMI. The easiest way to explain inverted AMI is to start with a digital signal you already know about. In an earlier program, you learned that the digital signals have only 2 states, on and off. A pulse represents a binary 1, and no pulse represents binary 0. This signal is called a unipolar signal because the pulses are always on the same side of the reference line. Devices that communicate using a unipolar signal over ordinary unshielded wire can't be more than about 50 feet apart. Otherwise, electrical interference picked up by the wire distorts the signal, and the receiving device can make errors interpreting it. To permit digital devices to communicate over longer distances, designers came up with the bipolar signal. This signal is usually referred to as the alternate mark inversion or AMI signal. The difference between the unipolar and the AMI signal is that in the AMI signal, the one's pulses alternate between positive and negative voltage. If the first binary one is a positive pulse, the next one that occurs in the bit stream will be a negative pulse, and the next one after that will be positive, and so forth. While the AMI signal permits the CPE devices to be further apart, solving one problem, there was another problem that still had to be addressed. As we will learn in a minute, the various devices that communicate over the S or T bus have internal clocks. They use these clocks to time the signals they transmit to the bus and to interpret the signals they receive from the bus. In order for the various devices to communicate, their clocks must be synchronized. This function is performed by the NT1. The other devices set their clocks using the pulses transmitted by the NT1. The problem is that at idle times on the bus, that is, when none of the devices are sending or receiving, very few pulses will be transmitted by the NT1. Even relatively brief periods of inactivity can cause the clocks to slip slightly. The solution to the problem is simple. You reverse or invert the signal states. Instead of the pulses representing binary ones, let the pulses equal zeros. Then, during idle states, you will be transmitting mostly pulses. When the devices are active, they will, on the average, be transmitting pulses half the time, so there will always be plenty of pulses from the NT1 for the other devices to use in keeping their clocks synchronized. Now that we know what the signal on the S or T bus looks like, the next question is, how do the various devices share the bus? We know that Lynn and Jim have BRI service that provides them with 2 B channels and 1 D channel. We know that they have 3 computers and 2 voice terminals that use these 3 channels at the same time, and that all this occurs over one S or T bus. How is this possible? The answer is that the devices share the bus using a combination of time division multiplexing and statistical multiplexing. Let's see how this actually works. Even when no devices are active, the NT1 transmits 192,000 bits per second over the S or T bus. 192,000 bits per second is the bandwidth of the S or T bus. Another way of looking at the bandwidth is to say that the S or T bus has 192,000 time slots, and that each time slot will contain a bit, that is, either a pulse, a binary 0, or no pulse, a binary 1. This bandwidth is divided into basic units called transmission frames. There are 48 bits or time slots in a transmission frame. Since the S or T bus has 192 kilobits per second bandwidth, if we divide by 48 bits, we see that there are 4,000 frames transmitted across the S or T bus each second. Each of the time slots in a transmission frame is reserved for one of 4 different types of bits. Bits going to or from a device that is using the B1 channel. Bits going to or from a device that is using the B2 channel. D channel bits. These bits will be part of a message containing signaling or packet information. These bits may be going to or from any of the devices. Overhead bits. These bits are scattered throughout the frame and serve a number of purposes, including synchronization and error checking. Notice that each transmission frame will contain 16 B1 channel time slots, 16 B2 channel slots, 4 D channel slots, and 12 overhead slots. The S or T bus is often referred to as a passive bus because it passively accepts whatever the various devices input to it. The devices themselves must be smart enough to know how to take turns using the bus, or chaos would result. Let's see how the devices accomplish this. Each device attached to the S or T bus has been designed and/or programmed to know 3 things: when each transmission frame starts, when each time slot starts, and how long it lasts. This is where clock synchronization applies. The NT1 defines the start of the time slot, and the other devices adjust their clocks to agree with the NT1. Which time slots in the transmission frame have been assigned to a device? For example, a D-channel device will pay attention to the information in the overhead time slots and, of course, to the D-channel time slots. It can ignore information in those time slots reserved for the B channels. When it needs to send information, it knows which 4 of the 48 time slots in the frame it can use. A voice terminal also pays attention to the overhead bits, but it sends and receives over both the D channel and one of the B channels. The ability of each device to receive or transmit only during its assigned time slots within a frame means that the various devices can share the bus without interfering with each other. This dividing up of the available time slots is known as time division multiplexing. When Lynn makes a call, the central office switch assigns a B channel to her voice terminal. Assuming her terminal is assigned to the B1 channel, the terminal will convert her analog voice signal to digital and input the bits to the B1 time slots in the transmission frames. It would monitor the B1 time slots on the incoming transmission frames, convert the bits to an analog signal, and output it through the speaker. Notice that in this example, only one device, Lynn's voice terminal, is transmitting and receiving over the B1 channel. If Jim makes a call while Lynn is still on the phone, the central office switch will assign his voice terminal to the B2 channel, but you still have one channel for one device. In fact, it is generally true that you have only one device per B channel. But what about the D channel? We know that Lynn and Jim have 3 PCs that share their D channel. We also know that the D channel is used to set up, monitor, and tear down calls on the B channels. How does all of this happen over one channel? To answer this question, we must go beyond time division multiplexing to a concept called statistical multiplexing. Statistical multiplexing is simply a priority ordering of D-channel functions and simple rules for determining which of the devices contending for the D-channel will dominate. There are two priority levels that define which of the contending devices gets to transmit over the D-channel. The highest priority is call processing data. Voice terminals need to send and receive messages over the D-channel to connect, monitor, and disconnect a B-channel call. These messages take precedence over any other use of the D-channel. Lower priority is for packet calls. Lower priority is given to transmission and receipt of packets and the setup or tear down of packet calls. All of the devices on the S or T bus monitor activity on the D-channel. When they see 8 consecutive D-channel time slots with pulses, that is binary zeros in them, this indicates that the D-channel is idle. The devices can then contend for the D-channel if they have messages to send. A voice terminal, being high priority, can start to transmit a message after 8 pulses. Once it has transmitted its message, it must wait 9 consecutive pulses, zeros, before it can transmit another message. This permits the other voice terminal to send a message if it has one to send. A low priority device must wait 10 consecutive pulses before it can send a message and 11 consecutive pulses before it can send each subsequent message. So far, we've been talking strictly about the signal on the S or T bus. What about the signal on the U interface that connects the NT1 with the line termination at the switch? And how do the B and D channel bits get transmitted across the U interface? Let's begin by looking at the transmission of bits and the U interface transmission frame. Remember that I said that the S or T bus transmission frame had 48 bits and that 12 of these were for overhead functions, such as synchronization and error checking. Well, the U interface transmission frame has 240 bits and 24 of them are needed for overhead. Let's compare the U interface transmission frame with the S or T bus transmission frame. One U interface frame contains the same number of B1, B2, and D channel bits as 6 S or T bus frames. The NT1 is responsible for converting S or T frames into U interface frames. To build a U interface frame, the NT1 first generates a standard 18-bit code called a synchronization word to mark the beginning of the frame. Then it inserts B1, B2, and D channel bits into the same order that they appear in the S or T bus frame, 8 B1 bits, 1 D bit, and so on until it has inserted the 216 B and D bits from the 6 S or T frames. Then it completes the frame with 6 overhead bits. Of course, the NT1 also converts U frames into S or T frames. We said that the bandwidth of the S or T bus was 192,000 bits per second, which is 48 bits per frame times 4,000 frames per second. There are only 666 2/3 frames per second transmitted over the U interface, but each frame has 240 bits. Multiplying 666.67 by 240 yields 160,000 bits per second, which is the bandwidth for the U interface. Until 1990, the characteristics of the signal that transmitted bits across the U interface were determined by the manufacturer of the central office switch. Many used an AMI signal similar to that used on the S or T bus. But while the bipolar AMI signal is better than the unipolar signal, it still places unacceptable limits on the length of the local loop. With AMI, under the best conditions, the NT1 can't be further than 8,000 or 9,000 feet from the line termination. As of 1990, however, the switch manufacturers have agreed to conform to one standard signal specification recommended by CCITT. This signal is referred to as 2B1Q. The 2B1Q signal extends the range between the NT1 and the switch to up to 18,000 feet. 2B1Q stands for 2 binary 1 quaternary, and it means that there are 4 signal states called quats, and that each quat represents 2 binary bits. To make sense of this, let's compare the inverted AMI signal used on the S or T bus with the 2B1Q. The inverted AMI signal has 3 signal states: positive pulse, which represents binary 0, no pulse, which represents binary 1, and negative pulse, which also represents a binary 0. The pulses alternate between positive and negative voltage, but this has no meaning. A positive pulse means the same thing as a negative pulse. With 2B1Q, there are 4 possible signal states, and the sign of the voltage as well as its magnitude has definite meaning. Each signal state represents 2 binary digits. One signal state is negative 3 volts, which represents binary digits equaling 0, 0. A negative 1 volt signal stands for the digits equaling 0, 1. Positive 1 volt equals 1, 1, and positive 3 volts equals 1, 0. I think that by now, you have a good idea of ISDN at the physical layer. You have seen how electrical signals carry information bit by bit between Lynn and Jim's CPE and their central office switch. Now let's turn our attention away from how information is transmitted and begin looking at what information is transmitted. The first layer of the OSI reference model that is concerned with the meaning of the bits transmitted is layer 2, the data link layer. Isdn protocols at the data link layer define the information that must pass between the CPE and the central office switch in order to establish and maintain an error-free link between them. These protocols also define how this information is organized into frames. Don't confuse the transmission frames that we discussed at the physical layer with the frames in the data link layer. Transmission frames define the time slots into which B and D channel bits could be placed. Data link layer frames define what bits must go into those time slots. There are 2 data link layer frames. The first is LAP-D frame, where LAP-D stands for Link Access Procedures for the D channel. It contains the information items that must be transmitted over the D channel for both B channel call control and D channel packet. There is a second data link layer frame type called the LAP-B frame. LAP-B means Link Access Procedures for the B channel, and this type of frame contains the items needed to transmit packet data over the B channel. The LAP-D and the LAP-B frames are very similar, so let's concentrate on the LAP-D. As you can see, the LAP-D frame begins with an 8-bit field called the start flag. The start flag is always a 0, 6 ones and another 0. The address field follows. This field is divided into subfields that indicate whether the frame is transmitting call control or packet information, whether it is transmitting a command or responding to a command, and the identification number of the CPE device that is sending or receiving the frame. The control field is next, and it indicates what type of frame this is. Some frame types require additional fields, and these fields will occur in the information area of the frame. There can be anything from 0 to 260 bytes or octets of information. If the frame is transmitting a packet, the packet goes into the information area. The next field in the frame is the Frame Check Sequence, or FCS field. The device that transmits the frame calculates a number based on all the other bits in the frame and inserts this value in the FCS field. The device that receives the frame also calculates the value, and if the 2 values do not agree, a transmission error has occurred. In this case, the frame would be retransmitted. The frame ends with an end flag, which contains the same 0, 6 ones, 0 code as the start flag. In fact, the end flag of one frame can also act as the start flag for the next frame. This concludes our discussion of the data link layer of communication. In the next program, we will discuss the third layer of the OSI reference model, the network layer. As you recall, the protocols at the network layer are concerned with defining the information that must be transmitted to establish and maintain an end-to-end connection. Please return to your computer to continue this lesson. Up to this point, we've talked about the physical level and described what the signals look like that transmit information between the CPE and the central office. You have learned how several CPE devices can share this transmission path. We have also talked about what information is necessary in order for a specific CPE device and the central office to establish a communications link, and how this information is organized into frames. In this program, we'll review what you learned earlier about packets and describe how they are transmitted in an ISDN environment. We will also go step by step through the processes that set up and tear down ISDN calls, both circuit switched and packet switched. Let's go on to the third layer of the OSI reference model, the network layer. As you recall, protocols at the data link layer are concerned with specifying how links are established between the customer's ISDN equipment, the CPE, and the network, the ET. Network layer protocols define the information that must be transmitted in order to establish and maintain an end-to-end connection between users. We said frames were the basic communication units at the data link layer. The basic communication units at the network layer are called packets or messages. Throughout the telecommunications industry, you will find the terms frame, packet, and message used interchangeably. This can be very confusing. In this course, we will be a little more precise. Packets and messages are always contained in the information field of a LAP-D frame. Messages contain the information needed to set up, monitor, and disconnect B channel calls. Packets contain the information necessary to set up and disconnect a packet call and the data itself. Both messages and packets have two major parts, header and information element section. The header identifies the type of message or packet, among other things. The kinds of information contained in the information element section and the length of the section are defined by the type of message or packet type. You may be asking at this point, okay, how do frames and messages work to process calls? Let's look at how an ISDN voice call gets connected. Jim is about to make a call. He is going to call Janet, one of his customers. Janet also has ISDN service out of the same central office as Jim. When Jim picks up his voice terminal, it generates a setup message, embeds it in a LAP-D frame, and sends it off on the D channel to the network termination, the line card on the central office switch. Since the voice terminal is a high priority device, this frame and the remaining call processing frames will have priority over any frames the PCs may be trying to transmit over the D channel. Also, since all messages on the D channel travel within LAP-D frames, I will take this for granted from here on. The processor is responsible for processing Jim's BRI service requests. This information identifies the exact nature of Jim's service, including what features are activated on his voice terminal and to which buttons on the set they are assigned. When the processor is ready to proceed with the call, it sends back a setup acknowledge message. This message tells the terminal to turn on the dial tone and collect the digits to be dialed. It also assigns the B channel to be used for this call, but the channel is not activated yet. As Jim presses the buttons on his keypad to input the number he is calling, the codes for these digits are assembled into information messages and transmitted to the LT. It may require several exchanges of information messages between the voice terminal and the switch before the processor has what it needs to set up the call. When all necessary information has been received and checked for errors, the switch sends back call proceeding messages. The switch establishes a route to Janet's local loop. Then it sends a setup message to Janet's voice terminal informing it of the incoming call and assigning a B channel. Janet's terminal sends back a call proceeding message, begins to produce the audible ringing tone, and sends back an alerting message, which is relayed to Jim's terminal. Upon receiving the alerting message, Jim's terminal generates the ring back signal. If Janet's terminal had been busy, a message would have been sent to Jim's terminal instructing it to generate the busy signal. When Janet answers, her terminal sends a connect message to the switch, which forwards it to Jim's terminal. Basically, this message tells the terminal that it's okay to stop the ringback tone and start transmitting and receiving voice signals over the assigned B channel. Then, the switch sends a connect acknowledge message back to Janet's terminal telling it to begin sending and receiving over its assigned B channel. Now the connection is complete and Jim and Janet can talk to each other. Let's assume that Jim, who's made the call, hangs up first. Jim's terminal sends a disconnect message to the switch. The switch sends a disconnect message to Janet's terminal and disconnects their two B channels. Because Jim originated the call, the switch immediately sends back a release message, which acknowledges that it received the notice to disconnect. If Janet had hung up first, the switch would have waited to receive the release message from Jim's terminal before sending a release message to Janet's terminal. The release of the B channel always begins with the terminal that hung up first. So Jim's terminal releases the B channel and then sends a release complete message to the switch. The switch then releases the facilities it was using to carry the call between Jim and Janet's line cards, and it sends a release complete message to Janet's terminal. When Janet's terminal receives this message, it releases the B channel it was using for the call. I've just given you an overview of how a voice call is connected and disconnected. Of course, instead of talking over the B channel, Jim and Janet could be sending data between their computers or their fax machines. So long as they were setting up a circuit-switched call, the procedure would be the same. But what if Lynn or Jim wanted to send an order to one of their suppliers using the public packet data network? Lynn has just finished inputting an order to her computer, and she is ready to send it on the packet network. We talked about packet switching in an earlier program. You learned that packets are sent and received by devices called Data Terminal Equipment, or DTE. When two or more DTE devices need to send packets to each other, a virtual call is set up. In a virtual call, lines and trunks are not dedicated to the connection between the DTE devices. Instead, primary and secondary routes between the DTE are defined during calls set up by telling each node or switching point along the routes where to send the packets for this virtual call. Lynn's computer has a personal computer terminal adapter, or PCTA, which means that the terminal adapter is built into her computer. The first thing that happens when Lynn turns on her computer is that it sends an LAP-D frame called an Activate Link frame to the switch. This tells the switch that the computer is ready to send and receive. The switch acknowledges with an unnumbered acknowledgement frame to say that it is also ready. When Lynn is ready to set up the virtual call, she enters the proper commands into her computer and it generates a LAP-D frame and embeds a call request packet in it. The frame address field indicates that this is a packet frame, not a call control frame, and identifies the device sending the frame. The packet header gives the data network address, or DNA, of the destination terminal, as well as Lynn's DNA. A DNA in the public packet data network corresponds to a telephone number in the public switch telephone network. It also provides other information required to route the packet to its destination, including the logical channel number, or LCN. What is a logical channel number? Let me explain it this way. Data terminal equipment with multiple ports sending packets over the D channel can have more than one virtual call established at the same time. The packet handler knows from the frame address which device has transmitted a packet, but it needs a unique number to identify which virtual call the packet belongs to. The LCN is this number. The LCN is used only for communicating between the DTE device and its packet handler. Once the computer assembles the call request packet, it is transmitted to the switch. The central office switch does some initial checking and sends the frame to the packet handler, or PH, which is the packet's entry point into the packet network. Depending upon who manufactured the central office switch, the packet handler may be part of the switch, or it may be a separate piece of equipment, perhaps located miles away. The packet handler establishes the routing and sends the call request packet on to its destination. When the call request packet reaches the packet handler at the destination end, this packet handler stores the appropriate routing information and assigns its own LCN number. This LCN is inserted in the packet. Then it is passed on to the proper DTE device at the destination, in this case, a computer at Lynn's supplier. Although the network didn't change the format of the call request packet, because it's at the destination end, it's now called the incoming call packet. If the supplier's computer is willing and able to establish a virtual call with Lynn's computer, it transmits a call accepted packet. This packet is transmitted to the packet handler at Lynn's end. The packet handler inserts the LCN, which is being used at this end. Then it passes the packet, which is now called the call connected packet, to Lynn's computer. Now, the virtual call between Lynn and her supplier is established, and the computers can begin sending data packets to each other. Because the routing information for this virtual call is stored in the packet handlers, there is no need to send the originating DNA, destination DNA, and other routing information in the data packets. The LCN is the only packet identification needed, so the header of the packet can be short and most of the packet can be used for Lynn's data. Each computer sends a count of the data packets it has sent and correctly received to the other computer. This assures that the packets being sent are being received without error. To end the virtual call, either computer sends a clear request packet through the network. It is called a clear indication packet at the destination end. This computer sends a clear confirmation packet to the other end. Both packet handlers erase the routing information from their memories, and the LCNs become available for assignment to another virtual call. We see that with virtual calls, routing information is held in the packet network memory only until the call is disconnected. There's another type of D-channel packet transmission service called a permanent virtual circuit, or PVC. With PVC service, the necessary routing information and assigned LCNs are placed into the permanent memory of both packet handlers. This service is useful when computers must transmit frequently. It eliminates the need to send call setup and disconnect packets for each data transmission session. A permanent virtual circuit must be ordered from the telephone company. There's one more type of packet transmission that should be explained. I said earlier that packets can also be transmitted over the B channel. The advantage of the B channel packet is speed. Packets are transmitted over the B channel at 19,200 bits per second, whereas on the D channel, the transmission rate is only 9,600 bits per second. The disadvantage is that at present, the B channel must be dedicated to packet transmission. It can't be used to send voice or data over the circuit-switched network. To obtain B channel packet service, Lynn would again order it from the telephone company. They would dedicate one of Lynn's B channels, say B1, to the packet handler. This means that instructions would be input to the switch to treat any messages on Lynn's B1 channel as packet messages and to route them to the packet handler. Lynn's computer could then establish virtual calls just as if it was on the D channel. It would use the same types of packets to set up the call, but these packets would be transmitted in the lap B frame, which is slightly different from the lap D frame. In the future, ISDN customers will be able to transmit packets on the B channel without having to dedicate it. They will be able to set up a virtual call on the B channel using messages sent over the D channel, just as they set up circuit-switched calls today. We reviewed how both circuit-switched and packet call processing occurs. That wraps up our discussion of ISDN call processing. Please return to your computer to continue this lesson.
It's impossible, without a genuine crystal ball, to find out just what the future holds for you or me. I certainly wouldn't want to predict just how our lives will have changed in 10 or even 5 years from now as ISDN evolves and becomes more widely available. But in this program, we'll start with what ISDN is today and take a look at the direction it's going. Then we'll speculate how living with ISDN could be in just a few short years. First, let's take a look at ISDN as it exists today. You already know that because ISDN offers multiple channels, you can have more than one voice and/or data call going on at the same time. This means that data users do not need a separate connection for their terminals. Because ISDN employs statistical multiplexing, up to 8 PCs or other devices can share the D channel. ISDN provides a digital signal from one user to the other. This means voice will be communicated with less noise and distortion. Data signals will be received with fewer errors. Because all ISDN signaling is carried on the D channel, the B channels can communicate at 64,000 bits per second, rather than 56,000. This means that circuit switch data is transmitted almost 15% faster. This increased bandwidth also makes possible compressed video for use in picture phones and teleconferencing. In general, ISDN will provide users easy access to high-speed networks, for example, to send fax or to transfer data files. ISDN uses the existing twisted pair wiring. This can simplify the installation of Isdn service, especially for residential and small business users. Attendant consoles also connect using twisted pair wiring instead of having special wiring requirements, such as a 25-pair cable. Not only is installation of the attendant console easy, but changing the attendant's location is greatly simplified. No special cable has to be rerouted to the new location. ISDN is defined by a set of international standards that are based on the Open Systems Interconnection concept. This means the ISDN customer premises equipment can be manufactured by many different vendors, and these devices will be compatible with the network, as well as with each other. That's quite a list of ISDN benefits. Simultaneous voice data, multiple devices, better voice, fewer errors, faster transmission, compressed video, simplified installation and rearrangement, equipment compatibility. And all of these benefits are available with ISDN as it exists today. But what about the future? Where is ISDN going? The future of ISDN centers around availability, coverage, bandwidth, and a concept called dynamic allocation. Let's look at each of these. As central offices replace their older switches with digital switches, and as digital offices upgrade their equipment and operating software, Isdn Services will become available to most telephone subscribers in the United States. This will mean that ISDN customers who are served by the same central office will enjoy the full capabilities of ISDN. But what about ISDN customers who wish to communicate between central offices and even across the country or across the world? That's what expanded coverage is about. We are now in Phase 2 of a three-phase evolution of ISDN. Phase 1 involved implementing ISDN in the major metropolitan areas in the United States and establishing a base of ISDN users. Phase 2 will involve establishing ISDN between offices within telephone companies' local exchange networks. Phase 3 will involve implementing ISDN across LATAs. This will involve both the local exchange carriers, the telephone companies, and the inter-exchange carriers, the long-distance service providers. The key to Phases 2 and 3 is the implementation of Common Channel Signaling System 7, CCS7. We've covered CCS7 in a previous program, but to refresh your memory, CCS7 is a method of transmitting the signaling information for call setup, monitoring and disconnection in a common channel that is separate from the channels over which the voice or data are being sent. By sending signaling information over a separate channel, one benefit is that all 64,000 bits per second of bandwidth is available for the voice or data. A third future development in ISDN is increased bandwidth. Increased bandwidth will mean better service for ISDN customers wherever large amounts of data or higher quality images, like high-resolution graphics or full-frame video, must be transmitted. We have discussed fiber optics in another program. You learned that transmitting at light frequencies permits a much higher bandwidth than is possible with any other transmission media in use today. Optical fibers will someday replace the twisted pair in the local loop. But even before this occurs, higher bandwidth will be available to ISDN customers by means of the H channels. Let's look at a video scene to see how increasing the bandwidth improves the quality of what you see. This scene was recorded by a video camera at 30 frames. That is 30 still pictures per second. Your video player is playing it back to you at that speed. This is referred to as full-frame video. Transmitting a full-frame video scene like this requires a bandwidth of 4.5 million bits per second, far more than the 64,000 bits per second available on a B channel. But there is a technique called compressed video that permits video transmission over the B channel. This is the same scene, transmitted at 64,000 bits per second, using compressed video. It's not very impressive, is it? But for scenes that don't change very much from frame to frame, like a picture of a head talking, or people in a meeting, the results are acceptable. But what if we have ISDN service with an H0 channel? You remember that the H0 channel basically combines the bandwidth of 6 B channels to provide 384,000 bits per second bandwidth. Our video would look like this, our talking head like this, and the meeting like this. Now what if we have Isdn service with an H11 channel, which combines 24 B channels to provide over 1.5 million bits per second? Our high-action video scene now looks like this. Quite an improvement, isn't it? But the low-action talking head has really improved, and so has the meeting. Unless compressed video technology improves, we probably will need a fiber local loop with its tremendous bandwidth for some video needs, but many video applications will require only the bandwidth that Isdn can provide over the existing wires. It is reasonable to predict that as bandwidth increases, so will the cost of Isdn service. A customer may need high bandwidth for only a limited period. For example, to conduct a teleconference for 2 hours every Monday morning. Naturally, this customer would not want to pay for the unused capability the other 99% of the week. A customer could order this service each week from the telephone company, but this is not a very efficient way of doing business. The fourth of our future Isdn developments, dynamic allocation, will resolve this problem. With dynamic allocation, our customer can change his Isdn service on a minute-by-minute basis, if necessary, simply by sending D-channel messages to the switch. For example, our customer, Smith Company, might have 2 PRI services, each with 23 B and 1 D channels, most of the time. On Monday morning, the company's Isdn system administrator can reallocate 1 PRI to an H11 channel to carry the teleconference. When the conference is completed, he can immediately change back to the original configuration. We know that Isdn is evolving toward greater availability, expanded coverage, increased bandwidth, and dynamic allocation. These future developments are quickly becoming reality. But just what might all of this mean for our working and home lives in a few years? As I said at the beginning of this program, it's hard to predict the future. Scientists and engineers continue to create new applications for Isdn. Let's do a little crystal ball gazing. Let's speculate on our future. We can be sure that Isdn will be found more and more in the workplace. However, the ease with which Isdn can be installed, its ability to simultaneously communicate voice and high-speed data, its compressed video capability, and its relatively low cost will mean that the workplace for more and more people will be in their own home. Instead of running out to the supermarket or the video store to rent a videotape, you can call in a selection and it will be transmitted to your TV over your Isdn service. Instead of going to the library, you will be able to identify pertinent references and download articles or even entire books into your computer. You can shop at home, and when you've worked up a good appetite, you can order something to eat. Your utility companies will be able to read your meters remotely using D-channel packet. Devices attached to your SRT bus can transmit D-channel packets warning of intrusion or fire to you at some other location, or to your security company. Today, such services require dial-up connections that are slower to respond and more expensive to operate. And the list could go on, but I think you're beginning to see something of the excitement that lies in the future of Isdn. This program reviewed the benefits of Isdn as it exists today and described some future developments. In the future, Isdn will have a large impact on our business and our personal lives. That concludes this video segment. Please return to your computer to continue this lesson.